Hello. And welcome back to the Umbrella Academy. We will now discuss E2 elimination from cyclohexane derivatives. Cyclic compounds follow same rules for E2 elimination, as does elimination from acyclic compounds. That rule is, anti-periplanar arrangement of two substituents that are being eliminated. This requirement has special significance when dealing with substituted cyclohexanes. Consider this mono-substituted cyclohexane. The substituent X occupies equatorial position and is more stable conformation than when the ring flips to put the X substituent on axial position. In this case, there are two beta positions with two hydrogens each carbon having an axial and an equatorial hydrogen. It is obvious that none of the hydrogens on either beta carbons are anti-periplanar to CX. Only C-C bonds denoted as 1 and 2 are anti-periplanar to CX bond. But these C-C bonds can't be removed by base. Thus, E2 elimination is not possible in this conformation though being more stable. However, in this less stable conformation, axial CX is anti-periplanar to axial hydrogens on either beta carbons. Thus, E2 elimination is possible through this less stable conformation. Thus, for E2 elimination in cyclic compounds, leaving group and beta hydrogen must be in 1,2 diaxial arrangement. For example, in case of this chlorocyclohexane. As said earlier, when chlorine is on equatorial position, it makes conformation more stable, but in this case none of the beta hydrogen are anti-periplanar to chlorine. Thus, base treatment of this conformation gives no E2 elimination. When ring flipping occurs to put chlorine on axial position, it makes this conformation less stable. Of the 4 beta hydrogens, encircled axial hydrogens on beta carbons are in desired anti-periplanar arrangement making E2 possible. We can show the mechanism of abstraction of axial beta hydrogen to form the cyclohexene product. Remember that, abstraction of axial hydrogen from either beta carbon gives the same product in this case. Consider this example, wherein trans-1-bromo-2-methylcyclohexane is treated with ethoxide base. 1,2-trans means 1,2 diaxial, or 1,2 diequatorial, out of which this diequatorial is more stable conformation. But, if we carefully observe this conformation, we see no anti-periplanar H on beta carbons, because bromine is equatorial. Thus E2 is not possible from this stable conformation. Ring flipping gives this diaxial conformation. With respect to bromine, 2 beta carbons are there. This beta carbon has only one hydrogen, which is equatorial and hence not anti-periplanar to axial bromine. This beta carbon has 2 hydrogens, one axial one equatorial. Only this axial hydrogen is anti-periplanar to bromine and is eliminated with bromine to form a double bond. Thus, this elimination doesn't follow the Zaitsev rule to form more substituted alkene. The reason is that, the elimination can occur only if the 2 substituents that are eliminated are in 1,2 diaxial arrangement. Thus, this axial hydrogen is eliminated even though it leads to formation of less substituted Hofmann product. We can write the product in planar form like this. And once you have understood how to apply the criteria and mechanism of elimination in substituted cyclohexane derivatives, you can write the product without going through chair conformations. For example, this beta carbon has methyl on dash, so the hydrogen must be on wedge. Likewise, this beta carbon has 2 hydrogens, one on wedge and other on dash. Since the bromine is on wedge, therefore, the 2 hydrogens shown on wedge are cis to bromine, and cannot be eliminated as per anti-periplanar requirement rule. Thus only this hydrogen on dash is trans and anti-periplanar to bromine, and can be abstracted by base to form this less substituted alkene product. So, the take-home message for E2 elimination of cyclohexane derivatives is that, atoms or groups to be eliminated must be in 1,2 diaxial trans arrangement, only then their orbitals are suitably oriented to overlap for the formation of pi bond. Now we will practice some E2 reaction examples. Consider this cyclic substrate. With respect to chlorine substituent, there are 3 beta positions. This beta carbon doesn't have any hydrogen. Thus, only two types of beta hydrogens are available and hence two products will be formed. Removal of beta hydrogen from ring gives this cyclic alkene, and removal of beta hydrogen from exomethyl gives this exocyclic alkene. This alkene is more substituted and hence Zaitsev product. This alkene is less substituted and hence Hofmann product. Zaitsev product will be major and Hofmann minor product. Consider this alkyl halide treated with potassium tertiary but oxide base. This is a bulky base. Substrate has 3 beta positions. The 2 beta positions inside the cyclic ring are similar. Tertiary but oxide is sterically hindered base, and will therefore prefer less sterically hindered beta hydrogen for abstraction to form Hofmann product as major product. Thus, removal of any of the secondary beta hydrogens from the cyclic methylene gives this alkene with double bond inside the ring, while the removal of primary hydrogen of methyl gives this exocyclic alkene. This cyclic alkene is more substituted and this exocyclic is less substituted. Thus, this is the minor and this is the major product upon treatment with bulky base. Consider the elimination of this cyclic chloride. This is called menthyl chloride. It has 2 beta carbons. This beta carbon has isopropyl group on wedge, therefore hydrogen must be on dash. Similarly, this beta carbon has 2 hydrogens. Let us put cyan blue hydrogen on wedge and red hydrogen on dash. This chlorine on alpha carbon is cis to this red beta hydrogen and this white hydrogen. Because both of these are also on dash. This chlorine on dash is trans to this cyan blue hydrogen on wedge. Therefore this will be eliminated on treatment with base to form this alkene product. Only one beta hydrogen is anti-periplanar to chlorine, therefore only one E2 product is possible. Take the similar isomeric molecule with chlorine cis to isopropyl group. Both shown on solid wedge here. This is called neomenthyl chloride. Thus, hydrogen on this beta carbon must be on dash. The other beta carbon has 2 hydrogen, cyan blue shown on solid wedge and red one, shown on dash. This chlorine and this cyan blue hydrogen, both are on solid wedge, which means they are cis to each other. And hence it cannot be eliminated with chlorine. This red and white hydrogen on dash are trans to this chlorine on wedge, and hence, both can be eliminated with chlorine to form 2 different alkene products. Elimination of white hydrogen with chlorine gives this alkene, and that of red hydrogen gives this alkene. This is more substituted, and this is less substituted. This is Zaitsev product, and this is Hofmann product. Zaitsev product, of course, will be major, and Hofmann will be minor product. In this example, these isomeric cyclic bromides undergo elimination at different rate. First one undergoes elimination slower than second one. We will go into mechanistic details to find the reason for this different rate of elimination. Let us take the first one. Bromine and methyl are trans to each other at 1 and 4 position. 1,4 trans means 1,4 diaxial or diequatorial. In the chair conformation, we keep both on equatorial positions, because diequatorial is more stable conformation. In this diequatorial, bromine being on equatorial means that E2 is not possible. Upon ring flipping, both bromine and methyl are axial. Now that bromine is axial, it means E2 can occur in this conformation. There are 2 beta positions each having axial hydrogen, which can be eliminated by E2. But this methyl in axial position makes this less stable conformation. Elimination of either axial beta hydrogen shown in red gives this product and of course it's enantiomer. Similarly take the second molecule, in which bromine and methyl are cis to each other. 1,4 cis means, one substituent on axial and other on equatorial. Let us keep bromine equatorial and methyl axial. In this conformation, bromine being on equatorial position means that no beta H is anti-periplanar to it, hence E2 is not possible. Ring flipping puts bromine axial and methyl equatorial. Bromine is now axial, means that E2 can occur in this conformation, as it has axial hydrogen on 2 beta carbons. Moreover, this methyl is equatorial, means that this conformation is relatively stable because methyl in essence is bigger than bromine. Now elimination of either red hydrogens will form this alkene product and its enantiomer. In the 1,4-trans isomer, the conformation from which elimination takes place has methyl axial, making it less stable, which is why elimination is slower than the beta elimination of 1,4-cis isomer, where the same methyl is equatorial, making it comparatively stable, which is why elimination is faster. If you don't want to miss out important lectures, then subscribe and press bell icon for notifications of new lecture uploads.